Welcome to EDU World Space.
So we're told a steel cable that is, let's see here, 3.5, 3 square centimeters is a cross-sectional area. It has a mass per unit length of 2.4 kilograms per meter, and there's 500 meters of it, and it's hung over a vertical cliff. And how much does a cable stretch under its own weight? And it's steel, so the Young's modulus is 200 gigapascals. So we have all our information here from the problem. And so what we need to do is we basically need to look at a little differential element of, this cable at some distance from the top. And so that differential element, we can see if we do a force balance on it, okay, we can see that we have some force here and some force here, and then we have the weight of it. And so the weight, we have a differential dm. I should probably write this a little bit different. Probably write it as GDM to make it a little more clear that we have a differential mass here. And so we know if we do a force balance here, we get that the force down here, the dF, the slight change in force, must be equal to minus GDM. And dm is I used here the actual mass density per unit volume. So then actually if you do that, then A's cancel out. But anyway, so this right here, A times dx is the volume of this, and then this is the volume density. Now if we integrate that, we can see that the force in the cable is a maximum at the top, and then when it gets to the bottom, it's going to be a minimum. So when x equals L, this should be 0, and because this is just GA rho times L, the mass, the basically just the weight of the cable. So what we can see here is that F is the force. So this is the let's see here, the stress times this, what am I saying? The strain. So we have the force. The force is the stress divided by the times the cross-sectional area, and the stress is the Young's modulus times the strain, which is dl dx. That's what I'm trying to say. So we can then separate variables and then integrate, and so we get y times a, and we go integrate from zero again from the change goes from 0 to L plus Li plus delta L. So that's we integrate over the whole length, the entire length. And then that equals, we integrate this, and this we just we can integrate this from 0 to Li, because x only was basically, well, it's hard to, x basically measures points in the wire. So basically, x's go from 0 to Li, and basically the x's get stretched. And so x is not the same as basically L. So you can kind of think of this as if you put marks on the wire, that would be, we're measuring marks by x, and we're measuring actually distance by L. So that's why we go only from 0 to Li over x. So we have the force times the length, and then minus this, the integral of this, and we just get x squared over 2. And over here we get y times Li times delta L. And what happens is these two guys cancel, and then we get that we can see that the A's drop out then, and then we have delta L equals 1/2 times the density per unit volume times G divided by the Young's modulus times the length squared. And if we change this to the density per unit length, the lineal density, then this is just lambda over A. So we wind up with the A back in here. And then we can plug in values, and we just get about 5 centimeters, or 4.9 centimeters for the change in length. So that's quite a bit, but again, it's a very long cable.